Today we are going to talk about factoring integers and get a little bit into a GCF. So that's our goal for today. We will talk more about GCFs on Monday. So for our warm-up, state whether 51 is divisible by 2, 3, 5, 6, 9, or 10. Use your rules. Is 51 going to be divisible by 2? Why not? Okay, it's not an even number, so it's definitely not divisible by 2. What about by 3? Yes, why is it divisible by 3? Very good. The sum of the numbers, so 5 plus 1 equals 6, and 6 can be divided by 3, so the number 51 can also be divided by 3. What about 5? No, why not? Very good. The 1's digit is not a 0 or a 5. Is it divisible by 6?
Yeah.
So I think this is one that I didn't realize it till the next hour. There was a typo in your notes, and I think I talked about it, but I didn't realize the typo was in your notes. It has to be divisible by both 2 and 3 to be divisible by 6.
Yeah.
So if in your notes it says 2 or 3, the word should be changed to and. So was it divisible by both 2 and 3? No, so 6 would not work.
And 10 is not because it's not 6.
What about 9?
Why do you say that?
Yeah, there's no 9.
Well, there's a 9 on the board, so we'll talk about it. Is it going to be divisible by 9?
No.
Why not?
Because it does not add it to the 9.
You're on the right track.
The sum of it doesn't add it to the 9. I mean, divisible by 9.
Okay, good. The sum of the digits is not divisible by 9. So if we were to add 5 and 1, we get 6. 6 is not divisible by 9. What about 10?
Nope.
Why not?
There's no 0.
Doesn't end in a 0.
That's the only
All right, questions on the first warm-up? All right, state whether 100 is divisible by 2, 3, 5, 6, 9, or 10. Is it divisible by 2? Yes, why? Okay, it's an even number. What about 3?
divisible by 3. No.
No. What's the sum of my digits?
1.
1. 1 plus 0 is 1. 1 is not divisible by 3. Is 100 divisible by 5? Yes. How do you know? Liam? Ends in 0, so it is divisible by 5. What about 6?
Nope.
No, because it needs to be divisible by 2 and 3, but it was not divisible by 3, so it can't be divisible by 6. What about 9? No, why not?
The digits are not divisible by 9.
Okay, if we add the digits up, we still get that 1. 1 is not divisible by 9. What about 10?
Yep.
Yes, because it ends in a 0. Questions about those divisibility rules from yesterday? Okay, we'll move into our notes. Ooh, too fast. In our notes, to factor a number over a given set, you write it as a product or multiplication problem of numbers in that set called the factor set. Anybody need more time with that? Okay, we talked a little bit about factors yesterday. So today we are going to start off by listing positive factors of each integer. So that means how could we write this number as a multiplication problem? My recommendation would be to always start off with the number 1. 1 times what would give you 56? 56. So 1 and 56 are both factors of 56. From there, I would start counting up and seeing if the number is divisible by the next whole number. And if it is, then you should be able to write a factor pair. Meaning, after 1, I would check 2. Is 56 divisible by 2? You guys are making me a little nervous. It's an even number, so is it divisible by 2? Yes. 2 times what would give me 56? 28. Is 56 divisible by 3? No, because 5 plus 6 is 11, so 3 would not belong on our list. So we check the next number, 4. Is 56 divisible by 4? You should be saying yes. If we check this off to the side, how many times does 4 go into 5? 1 times 4 is 4. Subtract, you get 1. Bring down the 6. How many times does 4 go into 16? 4. 4 times 4 is 16, which means we get a remainder of 0. So yes, 4 is a factor of 56. It would be 4 times. We just found it. 14. Okay, is 5 a factor? No. What about 6? No, it was divisible by 2, but not by 3, so 6 can't be on the list. Is 56 divisible by 7?
8 times 7?
8 times 7 is 56, so yes it is. You should know that one. Well, the rules help us for all of them, but we said we didn't have a rule for 7, so we just kind of have to check it. Okay, now if we were still counting up, the next number we would be checking would be 8, but we already found that pair. So once you loop back around, you can stop checking. Does that make sense? Okay, so we're counting up. So we did 1, 2, 3, 4, 5, 6, 7. The next thing we would check is 8, but that's just going to duplicate this problem. Does that make sense? We don't need to write it forwards and backwards. So that's how we know we can stop checking numbers. We found all of the factors. All right, let's try this again on number 2. We should always start with what? 1 and 48. After 1, we should check 2. 2 times 24. After 2, we should check 3. Is 3 going to work? Yes, because 4 plus 8 is 12. So 3 should work. 3 times what? 16. Okay, after 3, we should check 4. Is 4 going to work? Yes, 4 times 12. After 4, we should check. Will that work? Nope, so then we move on and check 6. Will 6 work? Yes, 6 times 8. Is 48 divisible by 7? No. 48 is not a multiple of 7. You should know that. And so the next number we would check would be 8, but it loops. It's already on there. Okay, so we know we're done checking. Seemed like that one went a little better. Are we getting the hang of this? Okay, for 100, I'm going to do that off to the side since I'm running out of space at the bottom there. So for 100, we start with 1 and 100, then 2 and 50. Should 3 go on our list? No. 4. 4 and what? 25. Good. 5. 5 times. 20. If you have 5 $20 bills, you have $100. Okay. Will 6 go on our list?
No.
7?
No.
8?
No.
Nope. 9?
Nope.
10?
Yep.
10 times
10.
10. You don't really have to write it with another 10, but you can if you want to. 10 times 10. Or just put a 10. Do we need to keep going? No, because we've technically already looped. Does that make sense? 10 loops on itself. Questions about finding the positive factors of an integer? You will have questions like this on your homework. A prime number is an integer greater than 1 that only has 2 factors, 1 and itself. So we should be filling in that definition. Notice that it has to be greater than 1, which means 1 is not a prime number. To find the prime factorization of a positive integer, you express it as a product of primes. In order to do that, we will make factor trees. So if you want to put a note off to the side by prime number, it's important to know 1 is not a prime number. And because of that, 1 does not go on factor trees. Which, if you're not familiar with factor trees, we'll talk about those on the next slide. So 1 is not a prime number. You will never write a 1 in a factor tree. Anybody need more time on this slide? Okay. So we need to find the prime factorization of each number. I will do them one at a time, so I've got a little bit of space to write. In order to make a factor tree, you are going to start with the number they gave you and branch it off into a pair of factors. Now remember, you cannot use 1, so you should not write 1 and 72. You can use any other factor pair. So 8 and 9 would work. That's not the only option. You have other options. But 8 and 9 is one option, because 8 times 9 equals 72. Are we all okay with that? Split it into one factor pair. You're going to keep doing that to your numbers until you only have prime numbers left. So is 8 a prime number? No, because it can get broken down into what? 2 times 4. Is 2 a prime number? Yes, so 2 is done. We're leaving that one alone. Is 4 a prime number? No, 4 can break down into 2 times 2. So now we know we're done with all of those. 2's are prime. But we got to jump over here to the 9. Is 9 prime? No. 3 times 3. Is 3 prime? Yes. So now we only have prime numbers at the bottom of our trees. So that means we could rewrite 72 as 2 times 2 times 2, because there were 3 2s. 2, 2, 2 times 3 times 3, because we had 2 3s. We get where I came up with this? We are not going to use numbers that we broke down. We only use numbers that are at the very bottom of the tree. So that means I will not write an 8, a 9, or a 4. We only write the prime numbers. If we broke it down, we don't write it. If we wanted to write this with exponents, I could put 2 to what power? The third power, and 3 to the second power. I would accept either way of writing this for a prime factorization. You could have it all expanded out, or you could write them with their exponents. Either one is fine with me. Questions about number 4? Okay, I'm going to take a little bit of it away to bring back number 5. Okay, we start off by breaking it into one factor pair. So what's something we know we could divide this by? 2, because it's an even number. So this could break into 2 and this should not be that hard. What's half of 50? What's half of 4? So half of 504 would be 252. Okay, 2 is prime, so we can leave it alone. 25. 252 is not prime. We could divide it again by 2. Now this one requires a little more brain power, but we should be able to take 252 divided by 2. $126. Okay, 2 again is prime, 126 is not. We could divide 126 by still an even number, so you could divide it by 2. 126 divided by 2 is 63. Okay, 63 is not prime. What could you divide it by? You got a couple options. 3. 3 times what would give me 63? How many times does 3 go into 6? 2 times. How many times does 3 go into 3? 1 time, so 21 times. 21 is not prime, so we can break down the 21 into I feel like some people might be saying it very softly. 7 and 3, or 3 and 7. Now, at the very bottom, I've got 2's, which are all prime, 3's, which are prime, and 7, which is prime. Remember, I'm ignoring any number that I broke down. So the original number and all these numbers that I broke down, I'm ignoring. So when I write my prime factorization, how many 2's do I have? 3 of them. So 2 times 2 times 2. How many 3's? 2 of them. 3 times 3. And what else do we have? 1, 7. So again, if you want to write this with exponents, you can. We don't have to put an exponent on the 7, but if we really wanted to, what would the exponent be? A 1. I'm fine with either form. So you could have it expanded out, or you could have it with the exponents. Questions, concerns? Need more time? All right, we're on to the back. A GCF, also known as a greatest common factor, is the greatest integer that is a factor of all given integers. Our hint is to find the matches. We'll talk about what it means by the matches in just a minute. Anybody still writing on this? Okay. Find the GCF of each pair. So what we're going to do, and there are a couple different ways of doing these. The way that works for all of them would be to do the prime factorization of each of them and then look at the matches between those lists. So these are pretty small numbers to do a prime factorization on. What could I break 12 into? Okay, we could do 2 times 6. 6 would break into 2 times 3. So for 12, I'll write it off to the side. 12, my prime factorization is 2 times 2 times 3. Let's do the same thing for 18. Okay, 2 times 9. 9 breaks into 3 and 3. So for 18, my prime factorization is 2 times 3 times 3. Once I have those lists, I'm looking for matches or pairs. What matches on those lists? Okay, we've got a match of 2s. We got a match of 3s. I don't really care which match you take. You could take the ones on the end or the one in the middle with the one on the end. So 2 times 3 would give me 6, so therefore that is the GCF of those numbers. So you look for the matches and multiply them together. But notice that for each match, we only used one of the numbers. So we had a match of 2s, we wrote down 1, 2. Match of 3s, wrote down 1, 3. The other way of doing that would be to write out all the factors for each number and look for the biggest number that you see on both lists. However, if we were to do that on a problem like number 8, where they give you numbers that are in the hundreds, that's going to get a little tricky. So let's try this method for number 7. What could I break 8 into? 2 and 4. 4 breaks into 2 and 2. Okay, so my list for 8 would be 2 times 2 times 2. For 24, what can I break into? What could I break into? Okay, 6 and 4. 6 breaks into 4 breaks into 2 and 2. So for 24, I've got 2 times 2 times 2 times 3. What do I have matches of? 2s. How many matches of 2s? 3 of them. So 2 times 2 times 2 is 8. So that is my GCF. Questions, concerns about calculating a GCF? Okay, let's do it for a pair of bigger numbers then. Let's find the GCF of 882 and 945. That means we need to break them down into their prime factorization. So if I take 882 I need a factor pair for it. Liam? Okay, 2 times 441. 2's prime, so I'll leave that alone. 441 will break down. Is 441 divisible by 2? Is it an even number? No, so it's not divisible by 2. Dominic, what is it divisible by? 3. Good. If we take 4 plus 4 plus 1, we get 9. That means this number is divisible by 3. Dominic, did you find the other factor that goes with it? Not yet.
Not yet.
Anybody find it? 147? Okay. 147, that's not divisible by 2, but it is going to be divisible by 3 again, because we add them up, we get 12. Everybody figure out what that one is? We can do the long division if we need to. What'd you get?
No, this doesn't make sense. This is like on an
Thank you. All right, 49 is not prime because it can break into 7 and 7. Okay, so now at the bottom we have all prime numbers. 2, 3, 3, 7, and 7 are all prime. So that's my list for 882. 2 times 3 times 3 times 7 times 7. Questions about that part of it? I still need to make my factor tree for what? 945. So now I'm going to have 945, and I need to break that down. What is something that is definitely divisible by? I think somebody said one of the options. 5 is one of the options. Definitely divisible by 5. What do we get if we divide it by 5? How many? What is it? That sounds about right. 189. 189 is divisible by 3 would work, yes. We divide 189 by 3, what do we get? Very good. 63 is not prime. It can be broken into what? 3 and 21. 21 can be broken into 7 and 3. Now all of our bottom branches are prime numbers. Remember, we ignore all the ones that we broke down. I would recommend writing these in order numerically. So like I'm putting my 3's first, then my 5, and then my 7. Once we have this list, we are looking for what? Matches or pairs of the same number. So what do we have matches of? 2 sets of 3s, 1 set of 7s. So 3 times 3 times 7 would give me what's 3 times 3? 9 times 7.
27. Wait, 9.
63. So 63 would be our GCF, greatest common factor of those two numbers. Yes.
What if we put
Okay. Anything else about this one before we move on? We got 3 more problems. So now we're doing kind of a review of all the different types of problems we've seen so far. First type of problem we did was listing positive factors. So this is kind of like what we did on the first couple examples, which means I should start with what number? 1 and 30. Then I would move on to what? And 15. After 2, I should check 3 multiplied by 10. Does 4 belong on the list? What about 5? 5 and 6. Do we need to keep going? No, because then we loop back around. We'd be making the same pairs. Questions on number 9? Okay, part of the struggle of this section for some students is that the problems are all just a little bit different. So if it says list positive factors, if you see the word list, start with your number 1. The next type, give the prime factorization. That's when we break it down with a factor tree and list out the numbers. Okay, so if I'm breaking down 98, what could I break it into? 2 and 49. 49 breaks into 7 and 7. Can anything break down further? No, because what number never goes on a factor tree? 1. So nothing else can be written or broken down any other way. So our prime factorization is 2 times 7 times 7, or 2 times 7 squared. Does not matter to me which way you write it. So if you see prime factorization, you need to make a factor tree. Questions, concerns, need more time with number 10. Okay, last one. Find the GCF of 66 and 90. These ones usually take the longest because you need to make 2 factor trees and then find the matches. So our factor tree for 66 shouldn't take us that long. What could I break it into? 6 and 11. Which one of those breaks down more? 6 breaks into 3 times 2. When I write my list, I would do it numerically. So 2 times 3 times 11. We also need to break down 90, 2 and 45. 45 breaks into 5 and 9. 9 breaks into 3 and 3. If it helps you, you could always cross off the numbers that you broke down so that you're not tempted to use them again. Which means on my prime factorization list, I would have 2 times 3 times 3 times 5. We look for matches. What do we have matches of? 2 and 3. 2 times 3 is 6, so that is my GCF.